Imagine staring into the night sky, knowing that among the countless twinkling stars, some hide secrets so strange they defy everything we think we understand about the universe. One of these enigmas lies in the faint, fading glow of white dwarfs, the dense, Earth-sized cores of dead stars. These cosmic ghosts should be quiet, predictable, their light dimming steadily as they cool over billions of years. But something bizarre is happening. Astronomers have detected signals from these stellar remnants that shouldn't exist: pulses of energy, strange fluctuations, and mysterious emissions that leave even the brightest minds scratching their heads. White dwarfs are the final stage of life for most stars, including our own sun. After exhausting their nuclear fuel, they collapse into incredibly dense objects, packing a sun's worth of mass into a sphere no bigger than Earth. Their physics should be straightforward, their behavior predictable, yet time and again, observations reveal anomalies that challenge our textbooks. Some flicker unpredictably, others emit unexpected bursts of radiation, and a few even seem to have structures around them that defy explanation. These aren't just minor quirks, they're cosmic puzzles pointing to phenomena we can't yet explain. What if these signals are messages from the universe, clues to processes we've never imagined? Over the years, astronomers have catalogued 25 of these unexplained emissions, each one more baffling than the last. Some suggest hidden companions, like rogue planets or neutron stars lurking unseen. Others hint at exotic physics, like crystallizing cores or magnetic fields stronger than anything in our solar system. And then there are the ones that simply refuse all explanation, leaving scientists to wonder if we're missing something fundamental about how the universe works. This journey takes us to the edge of known science, where every strange signal could rewrite the rules. Strap in, we're about to dive into the 25 most mysterious signals from white dwarfs, and by the end, you might just question everything you thought you knew about the cosmos. The first signal on our list is one that sent shockwaves through the astronomical community, a repeating radio pulse ticking away with eerie precision from the vicinity of a white dwarf. Unlike the chaotic bursts we often see in space, this one arrived like clockwork, pulsing at intervals so regular it almost seemed artificial. At first, researchers wondered if they were seeing some kind of cosmic lighthouse, a natural beacon flashing in the depths of space. But the more they studied it, the stranger it became. White dwarfs aren't supposed to emit strong radio waves, let alone rhythmic ones. Their quiet, cooling cores shouldn't produce these kinds of energetic outbursts. So what could be causing it? One leading theory involves extreme magnetic fields. Some white dwarfs possess magnetospheres so intense they can accelerate particles to near light speeds, generating powerful radio emissions. But even then, the perfect timing of these pulses is hard to explain. Could it be some kind of interaction with an unseen companion, a neutron star or a rogue planet, locked in a tight orbit, stirring up the white dwarf's magnetic field like a spoon swirling in a cup? Then there's the more speculative but tantalizing possibility. Could these pulses be artificial in origin? The idea isn't as far-fetched as it sounds. Scientists have long considered the potential for advanced civilizations to harness stellar remnants as energy sources or even communication beacons. The regularity of the signal does echo what we might expect from an engineered transmission. Of course, extraordinary claims require extraordinary evidence, and most astronomers lean toward natural explanations. But the fact that this question even arises shows just how bizarre this signal truly is. What makes this mystery even more compelling is that this isn't the only white dwarf sending out repeating radio pulses. Several others have been found, each with its own peculiar rhythm. Are we looking at a common but unknown astrophysical phenomenon, or is each one a unique cosmic oddity? Until we uncover more, these pulses remain one of space's most perplexing enigmas, a cosmic metronome ticking away, daring us to decipher its secret. The discovery of this rhythmic radio pulse sent astronomers scrambling to their telescopes, desperate to confirm what they were seeing wasn't some glitch in the data. Teams across multiple observatories redirected their instruments toward the mysterious White Dwarf, turning some of humanity's most powerful eyes on the sky toward this cosmic oddity. The Arecibo Observatory, before its tragic collapse, played a key role in verifying the signal's existence, while newer facilities like the Very Large Array in New Mexico helped rule out interference from earthly sources. Each new observation only deepened the mystery as the signal persisted with that same unnatural regularity. Within the scientific community, reactions ranged from cautious skepticism to outright excitement. Some researchers immediately pointed to known astrophysical phenomena as potential explanations. Could this be a new type of pulsar white dwarf binary system, where the dense remnant star gets whipped into emitting radio waves by an unseen neutron star companion? Others suggested it might be evidence of a previously unobserved interaction between a white dwarf's intense magnetic field and a debris disk of planetary remnants. But even these explanations left gaps. None could fully account for the signal's precision and power. The debate grew heated at conferences, with papers flying back and forth arguing for and against various theories. Then came the wildcard hypothesis, the one that made headlines beyond scientific circles. A small but vocal group of researchers floated the idea that we might be looking at evidence of extraterrestrial technology. They pointed to the signal's artificial seeming regularity, drawing comparisons to humanity's own early radio transmissions. The scientific establishment pushed back hard, emphasizing that extraordinary claims require extraordinary evidence. But the idea stuck in the public imagination, fueled by decades of science fiction and our enduring fascination with the possibility of cosmic neighbors. What's fascinating is how this single signal forced astronomers to revisit old assumptions. White dwarfs were supposed to be quiet, predictable celestial objects. This discovery proved they could still surprise us. The controversy also highlighted how little we truly understand about the later stages of stellar evolution. If a dying star's corpse could produce something this baffling, what other cosmic secrets might we be missing? The telescopes kept watching, the data kept accumulating, but the answer remained just out of reach, an enduring cosmic riddle written in radio waves from beyond the grave of a star. As researchers continue monitoring this and similar signals, new technologies offer hope for answers. Next-generation radio telescopes like the Square Kilometre Array promise unprecedented sensitivity to detect fainter signals and potential companion objects. Meanwhile, advances in computer modeling allow scientists to simulate increasingly exotic stellar scenarios. Yet for now, the White Dwarf's rhythmic pulses continue their mysterious cadence, a cosmic drumbeat that may either rewrite astrophysics textbooks or, just possibly, introduce us to something even more profound about our place in the universe. The one certainty is that when nature throws us a curveball this dramatic, the discoveries that follow tend to reshape our understanding of reality itself. Just when astronomers thought white dwarfs couldn't get any stranger, another signal shattered expectations, a violent flicker of X-rays bursting from an otherwise calm stellar remnant. Unlike the steady radio pulses we just discussed, this phenomenon was chaotic and erratic, flashing unpredictably like a cosmic strobe light. The event lasted mere minutes, but its intensity was staggering, releasing more energy than our sun produces in weeks. What could possibly cause such a sudden, violent outburst from a star that's supposed to be quietly fading into oblivion? The leading explanation points to something lurking in the shadows, an invisible partner in this celestial dance. White dwarfs sometimes exist in binary systems, and if this one had a companion star or even a massive planet, material could be slowly stripping away from that object and falling onto the white dwarf's surface. This process forms what's called an accretion disk, a swirling, superheated ring of matter spiraling inward at nearly the speed of light. Normally, these disks release energy steadily, but under certain conditions they can become unstable. Imagine water building up behind a dam until the pressure becomes too much, causing a catastrophic release. That may be what happened here, with pent-up material suddenly plummeting onto the White Dwarf in a searing X-ray burst. But there's another, more dramatic possibility. Could this have been the aftermath of a cosmic collision? Some researchers speculate that the White Dwarf might have plowed through a dense cloud of interstellar debris or even smashed directly into a rogue planet. The sheer force of such an impact would generate staggering temperatures, easily explaining the intense X-ray flare. Supporting this idea are observations of similar outbursts around other white dwarfs, some with strange chemical signatures in their atmospheres, hints that they've recently consumed rocky bodies. Then there's the wild card, quantum phenomena. White dwarfs are so dense that their interiors may undergo strange phase transitions as they cool, with their carbon cores potentially crystallizing into cosmic diamonds over billions of years. Could some internal seismic shift, a starquake in this crystallizing core, have triggered a massive release of energy? It's a fringe theory, but not impossible. The truth is, we've only just begun to understand how matter behaves under these extreme conditions, and every unexplained burst forces us to reconsider the physics of these stellar corpses. What makes this particular signal so fascinating is that it wasn't a one-time event. Since its discovery, several other white dwarfs have exhibited similar flickering X-ray bursts, each with slightly different characteristics. Some recur at irregular intervals, while others flare once and vanish back into obscurity. This tells us we're likely looking at a common but poorly understood aspect of white dwarf behavior, one that might hold clues to how these objects interact with their environments long after their star-forming days are over. Until we catch one of these outbursts in the act with next-generation X-ray telescopes, the mystery will continue to simmer, a reminder that even in death, stars refuse to go quietly. While the X-ray bursts themselves were shocking enough, what truly baffled scientists appeared when they analyzed the light signatures, the spectral fingerprints of these violent events. The telescopes recorded lines in the spectrum that simply shouldn't exist, revealing chemical signatures that defied all expectations. Spectral analysis is normally straightforward, with each element producing telltale lines at specific wavelengths like a cosmic barcode. But these didn't match anything in our databases, sparking a frantic scramble to explain what we were seeing. At first, researchers wondered if they discovered some exotic new form of matter. White dwarfs are extreme environments where atoms get crushed under incredible pressures, their electrons squeezed into bizarre configurations. Could this have created strange, compacted states of matter we've never observed in laboratories? Some theories pointed to electride structures, atoms so compressed they shed their outermost electrons, forming a sort of electron soup permeating the material. Others suggested the spectral lines might come from super-heavy elements forged in previous stellar explosions, isotopes so unstable they only exist fleetingly in these extreme conditions. Then came an even more radical idea. What if these lines weren't from elements at all? White dwarfs with strong magnetic fields can distort atomic energy levels in ways that shift spectral lines dramatically, a phenomenon called the Zeeman effect on steroids. The most magnetized white dwarfs have fields millions of times stronger than Earth's, capable of bending light and altering emission signatures beyond recognition. If this was the case, we might not be looking at unknown elements, but familiar ones behaving in utterly unfamiliar ways under forces we can barely replicate. The implications reach far beyond a single stellar corpse. If these spectral lines do represent new states of matter, they could rewrite parts of quantum physics, showing us how particles behave under conditions so extreme they border on the unimaginable. Alternatively, if they're evidence of previously unseen elements, they might hint at undiscovered chapters in stellar nucleosynthesis, the cosmic process that builds heavier atoms inside stars. Either way, these anomalous lines force us to confront how much we still don't understand about the universe's most fundamental building blocks. What makes this mystery particularly tantalizing is that these spectral oddities aren't isolated to one event. Several white dwarf outbursts have now shown similar unexplainable lines, each with slight variations that suggest a complex underlying phenomenon. Some researchers propose we're seeing the fingerprints of shredded planets or asteroids, their diverse mineral compositions vaporized and reconfigured under the white dwarf's crushing gravity. Others argue we might be observing the aftermath of nuclear reactions in the star's outer layers, where residual hydrogen could be fusing in unpredictable ways. As telescopes grow more sophisticated, capturing these fleeting spectral signatures with greater precision, we may finally crack this puzzle. But for now, these unidentifiable lines serve as a humbling reminder that even with all our knowledge, the universe still holds cards it hasn't yet revealed. Each anomalous wavelength is like a whisper from the cosmos, hinting at physics beyond our current understanding, waiting for the right mind to decipher its meaning. Deep in the infrared spectrum, astronomers spotted something that shouldn't exist. A faint, warm glow surrounding a white dwarf like a ghostly halo. These stellar remnants are supposed to be cold, darkening embers, their heat slowly bleeding away into space over billions of years. Yet here was one radiating inexplicable infrared light, as if something unseen was gently warming its surroundings. The discovery sent researchers scrambling for explanations, because this wasn't just a minor anomaly. It was a fundamental challenge to how we understand these cosmic tombstones. The leading theory points to a cosmic crime scene. When stars die, their planetary systems don't always go quietly. Some white dwarfs are surrounded by dusty debris disks, the mangled remains of asteroids, comets, or even planets torn apart by the star's immense gravity. As these fragments collide and grind into dust, they heat up just enough to emit infrared radiation. It's a plausible explanation, except for one problem. The glow around this particular white dwarf was too uniform, too smooth, unlike the clumpy, irregular emissions we'd expect from a chaotic debris field. That's when another possibility emerged: an invisible companion. Imagine a dim, failed star like a brown dwarf or even a gas giant planet locked in a slow dance with the white dwarf. The companion's own heat could explain the infrared signature, especially if it's being gently cooked by the white dwarf's residual warmth. Some researchers even speculate about more exotic partners, like a rogue planet recently captured by the star's gravity, its atmosphere slowly evaporating under the intense radiation. But searches for such companions have come up empty, leaving the infrared glow frustratingly unresolved. Then there's the wildest idea of all, a phenomenon called dark matter heating. If dark matter particles interact with the white dwarf's dense core, they could theoretically deposit energy as they collide with atoms, creating a subtle infrared glow. It's a long shot, but the fact that scientists are even considering it shows how perplexing this signal truly is. The truth may be even stranger than we've imagined, hiding in the quiet whisper of infrared light from a star that's already dead. What makes this mystery so compelling is that it's not isolated. Multiple white dwarfs now show similar unexplained infrared excesses, each with slight variations that hint at a complex underlying process. Some flicker unpredictably, while others maintain a steady glow over decades. Could we be seeing different stages of the same cosmic process, perhaps the gradual disintegration of planetary systems or the slow awakening of some hidden stellar mechanism? The answers might rewrite our understanding of how star systems evolve, even in their final, fading moments. As telescopes like the James Webb Space Telescope turn their infrared eyes toward these enigmatic stars, we're poised for breakthroughs. Every new observation peels back another layer of the mystery, revealing just how little we know about the afterlife of stars. That faint infrared whisper isn't just heat, it's a message from the cosmos waiting for us to decode its secrets. Debris disks around white dwarfs shouldn't be this puzzling after all. We've seen similar rings of dust and gas around young stars forming planets, but when these structures appear around stellar corpses, they rewrite the rules. The conventional view was simple. When a star like our Sun dies, its violent death throes should obliterate or fling away any surrounding material. Yet here we are, finding these pristine disks of debris orbiting white dwarfs as if the apocalypse never happened. How does anything survive the star's catastrophic transformation into a white dwarf? The answer might lie in the ruins of planetary systems. Imagine the chaos when a star expands into a red giant, swallowing its inner worlds before collapsing into a white dwarf. The gravitational upheaval would send surviving outer planets careening wildly, smashing asteroids and comets into dust. This pulverized material could then settle into a disk, slowly spiraling inward as the white dwarf's gravity feeds on the remains. But here's what's strange: some of these disks contain elements we'd only expect from rocky planets like oxygen, silicon, and iron. That suggests these white dwarfs aren't just snacking on asteroids, they might be consuming the shattered cores of entire Earth-like worlds. Even more baffling is how orderly these disks appear. Instead of the expected chaotic rubble, some show finely ground dust distributed almost like a smooth, glowing sheet. One leading explanation involves collisions so frequent that debris gets sandblasted into ultra-fine particles. But that still doesn't fully explain why some white dwarfs have disks while others, even those in similar environments, show no trace. Could there be unseen forces at play, like hidden planets shaping the debris into these precise formations? Some researchers think so, pointing to subtle gravitational disturbances that hint at surviving worlds still orbiting these dead stars. The biggest shock came when astronomers found disks with chemical compositions that matched nothing in our solar system. Certain white dwarfs show bizarrely high concentrations of lithium, calcium, or even unexpected metals like gold, elements that shouldn't be so abundant in typical planetary debris. One theory suggests we're seeing the remains of exoplanets with radically different geology than anything we know. Another, more startling idea proposes that some white dwarfs are actively separating elements, with heavier metals sinking toward their cores while lighter materials remain suspended in the disk. If true, this would mean dead stars are still chemically processing their surroundings long after their nuclear furnaces have gone dark. Perhaps the most unsettling implication is what this means for the fate of our own solar system. The presence of these disks suggests that even after the Sun's death, some remnants of Earth might persist not as a planet, but as a ghostly ring of vaporized rock slowly raining down onto the white dwarf it once orbited. The same metals in our mountains, the same silicates in our beaches, could one day form part of a glowing disk around the Sun's corpse. It's a humbling thought that even in death, stars might preserve echoes of the worlds they once nurtured. As telescopes continue studying these disks in ever greater detail, each observation peels back another layer of mystery. Some show unexpected gaps, like cosmic breadcrumbs hinting at unseen planets still clinging to existence. Others flicker unpredictably, as if their structure changes daily. Whatever the explanation, one thing is clear: white dwarfs aren't just dead stars. They're cosmic archaeologists preserving, and sometimes actively reshaping, the remnants of the planetary systems they once ruled. And every strange signal from these disks forces us to reconsider what happens when a star's light fades, but its legacy refuses to disappear. Gravity waves ripple through the fabric of spacetime itself, usually born from the most violent cosmic events colliding black holes, merging neutron stars, the unimaginably powerful deaths of massive stars. So when detectors picked up a gravitational wave signal tied to a white dwarf, physicists did a double take. These stellar remnants shouldn't be capable of creating such ripples. They're the quiet old age of stars, not the cataclysmic powerhouses that warp spacetime. Yet the signal was unmistakable, a faint but distinct tremor in the universe's structure, traced back to a white dwarf doing something it had no business doing. The strangest part, this wasn't a collision. Gravitational waves from black holes or neutron stars come from their final, frantic moments before merging, sending shockwaves across the cosmos. But this white dwarf was alone, no partner in sight. What could possibly make a solitary, cooling star corpse shake spacetime? One possibility is a runaway explosion on its surface. White dwarfs occasionally experience thermonuclear eruptions when accumulated hydrogen ignites in a runaway reaction. These bursts can be violent enough to briefly outshine entire galaxies. But could they really be strong enough to generate gravity waves? Most models say no unless there's something fundamentally wrong with our understanding of these eruptions. Then there's the more unsettling explanation, hidden structure inside the white dwarf itself. These stellar remnants are unfathomably dense, with matter packed so tightly that a teaspoonful would weigh as much as an elephant. Under those extreme pressures, matter behaves in ways we can't replicate in any lab. Some theories suggest white dwarfs might develop exotic internal layers as they cool crystalline lattices of carbon and oxygen, or even stranger quantum states. If part of that structure suddenly shifted like a continental plate slipping in an earthquake, could it send ripples through space-time? It's a radical idea, but the signal demands radical explanations. Perhaps the most mind-bending possibility involves dark matter. If certain types of dark matter particles accumulate inside a white dwarf over billions of years, they might eventually reach a critical density and annihilate in a sudden burst of energy. The resulting explosion would be invisible to telescopes, no light, no X-rays, but the gravitational shockwave could theoretically match the signal we detected. It's a long shot, but if proven true, it would be our first direct evidence of dark matter interacting inside stars. What makes this discovery so transformative is that it forces us to reconsider what white dwarfs are capable of. For decades, we've treated them as straightforward endpoints of stellar evolution, simple, inert cores slowly fading to black. But if they can generate gravity waves, they might be far more dynamic than we ever imagined. Every new detection could reveal another layer of complexity, another way these dead stars continue to shape the universe long after their lights go out. The implications stretch beyond white dwarfs too. If something as seemingly placid as a cooling stellar remnant can produce measurable spacetime ripples, what else have we been overlooking? Are there other quiet corners of the cosmos hiding gravitational surprises? Future observatories like the Laser Interferometer Space Antenna might detect hundreds of these signals, each one a clue to the hidden lives of stellar corpses. For now, this lone gravity wave stands as a tantalizing mystery, a whisper from a dead star proving that even in stillness, the universe never stops moving. When LIGO first detected the gravitational wave signal matching a white dwarf, the team initially assumed it must be some kind of error. The observatory was designed to catch collisions between massive objects like black holes, not subtle ripples from solitary stellar remnants. Engineers ran diagnostics checking for instrumental glitches or environmental interference, but the signal persisted, its waveform clearly etched in the data. The frequency was all wrong, too much lower than the high-pitched chirps of neutron star mergers, more like a slow, ponderous thump in the fabric of spacetime. This wasn't just an anomaly, it was a direct challenge to our understanding of white dwarfs' capabilities. The immediate assumption was that the white dwarf must have a hidden partner. Perhaps two white dwarfs were spiraling toward collision, their dance generating gravity waves as they inched closer. But follow-up observations revealed no companion, no telltale wobble in the star's motion, no flickering light from an orbiting body. The white dwarf appeared completely alone, yet somehow shaking the universe around it. Theorists scrambled, digging through decades of stellar models for any overlooked phenomenon that could explain the signal. One faction argued for an internal cataclysm, a sudden rearrangement of the star's crystallizing core, like an earthquake echoing through its ultra-dense structure. Others proposed a more unsettling idea, that the white dwarf had briefly turned into a pulsar. Pulsars, rapidly spinning neutron stars with lighthouse-like beams of radiation, are known to emit gravitational waves if their rotation becomes lopsided. But white dwarfs aren't supposed to spin fast enough for that, unless perhaps this one had been kicked into hyperdrive. Imagine a white dwarf gaining sudden angular momentum, maybe from swallowing a rogue planet or being sideswiped by another star. Calculations showed that under extreme conditions, a white dwarf spin could theoretically cross a threshold where its shape distorts enough to ripple spacetime. The math was speculative, but it fit the data better than any other explanation. Then came the curveball. Months after the initial detection, archival data from other observatories revealed something astonishing. A faint X-ray flare from the same region of space, timed just hours before the gravity wave signal. The coincidence was too precise to ignore. Could the two events be connected? One hypothesis suggested a magnetic reconnection event, where the white dwarf's monstrous magnetic field lines snapped and realigned, triggering both the X-ray burst and a gravitational tremor. Another team proposed that the white dwarf had briefly reignited nuclear fusion in its outer layers, creating a shock wave that reverberated through its interior. The implications are staggering. If white dwarfs can produce gravity waves through mechanisms we've never considered, it means these stellar corpses are far more dynamic than we imagined. Future detections could reveal an entire hidden population of active white dwarfs quietly warping spacetime in ways that rewrite the textbook. LIGO engineers are already adjusting their algorithms to hunt for similar low-frequency signals, while astrophysicists are racing to model these bizarre new behaviors. Every unexplained ripple carries a message. Even in death, stars still have secrets to share. Some white dwarfs refuse to play by the rules, and one in particular has left astronomers utterly baffled with its erratic, shape-shifting magnetic field. Normally, these stellar remnants should have magnetic fields that weaken predictably over time as the star cools and its charged particles slow down. But this one bucks all expectations, with measurements showing its magnetic strength surging and plunging like a roller coaster, sometimes doubling in intensity before collapsing again within mere decades. That's an eye blink in cosmic terms, far too fast for any known process in a white dwarf's life cycle. What makes this behavior so startling is how it contradicts everything we thought we knew about magnetic field decay. Imagine a bar magnet left alone in a vault. Its pull weakens gradually over centuries as its atomic alignment frays. White dwarfs should follow the same pattern, their magnetic fields fading smoothly as they cool. Instead, this star's field behaves like a living thing, flickering unpredictably, almost as if something inside is actively regenerating it. One theory suggests hidden dynamo action, a churning layer deep within the white dwarf where currents could regenerate the magnetic field like a cosmic generator. But white dwarfs aren't supposed to have the internal heat or movement to sustain such dynamos, unless perhaps their cores aren't as dormant as we assume. Then there's the possibility of external interference. Some researchers speculate the white dwarf might be plowing through interstellar clouds, with ionized gas compressing and twisting its magnetic field lines into temporary knots. Others wonder if an undetected companion, a neutron star or black hole, could be warping the field through gravitational tides. The most tantalizing and controversial idea involves quantum effects in the white dwarf's core. As it cools, the hyper-compressed matter inside might undergo phase transitions, rearranging into crystalline structures that sporadically release pent-up magnetic energy like a coiled spring snapping. The implications reach far beyond this one oddball star. If white dwarfs can regenerate their magnetic fields, it means these stellar corpses might have unexpected inner lives. Some could even harbor hidden engines of magnetism that delay their cosmic fade out by billions of years. Future telescopes may reveal this isn't an anomaly, just the first glimpse of a phenomenon that's been hiding in plain sight all along. Every erratic pulse of its magnetic field is a challenge to our models, a dare to reconsider what we assume about the quietest stars in the universe. What's truly humbling is how little we still grasp about these fading embers. For all our theories, the universe keeps tossing curveballs like a white dwarf that forgot it was supposed to die quietly and instead began rewriting the rules of magnetism from beyond the grave. The starquake hypothesis offers one of the most compelling and dramatic explanations for these erratic magnetic fields. Picture this: a white dwarf's core isn't just a homogeneous blob of cooling matter. As it ages, the unimaginable pressures inside begin forcing atoms into a crystalline lattice, like a diamond the size of a planet solidifying in slow motion. But this process isn't smooth. The star's crust, now rigid and brittle, can't flex to accommodate shifts in the crystallizing core beneath it. Tension builds until, crack, the entire outer layer fractures in a catastrophic stellar earthquake. The energy released wouldn't just jolt the star, it could violently reorganize its magnetic field, explaining those sudden surges and drops in intensity. These quakes wouldn't resemble anything on Earth. A white dwarf's crust is ultra-dense material, harder than any substance we know, snapping under pressures billions of times stronger than our planet's tectonic shifts. The resulting tremors could ripple through the star at relativistic speeds, rearranging its magnetic architecture in hours. There's precedent for this. Neutron stars, the denser cousins of white dwarfs, are known to produce starquakes that alter their spin and magnetic signatures. If white dwarfs experience similar events, it would rewrite our understanding of their internal dynamics. What makes this theory so elegant is how neatly it ties together multiple mysteries. Those bizarre X-ray bursts we discussed earlier, they could be the flash of energy released during a quake. The unexplained spectral lines, perhaps the signature of heavy elements churned up from the star's depths during these upheavals. Even the gravitational wave signal might fit. A particularly violent quake could momentarily distort the white dwarf's shape enough to ripple spacetime. Suddenly, phenomena we thought were unrelated start forming a coherent picture of these stars as restless, ever-changing objects. But here's the catch: we've never directly observed a white dwarf starquake. The hypothesis relies on computer models and indirect evidence, like how a seismologist might infer an earthquake's properties from distant tremors. Some critics argue that white dwarfs simply aren't dynamic enough to produce quakes of this magnitude. Others counter that we've been looking at the wrong timescales. These events could be rare, occurring once every few centuries, making them easy to miss in our brief window of observation. The most tantalizing possibility is that starquakes aren't isolated events, but part of a larger cycle. As a white dwarf cools, its core might undergo repeated phase transitions, each one triggering quakes that revive its magnetic field like a cosmic defibrillator. This would mean these stellar corpses aren't fading quietly at all. They're spasming through violent metamorphoses, their magnetic lives extended far beyond what we thought possible. Future telescopes capable of detecting subtle vibrations in white dwarfs' light could finally settle the debate, revealing whether these cosmic tremors are fact or fiction. Until then, the starquake hypothesis remains a brilliant but unproven solution, one that reminds us how even the quietest stars might still be shaking beneath the surface. Astronomers tracking a seemingly ordinary white dwarf got the shock of their careers when its light curve, the steady graph of its brightness over time, suddenly flatlined. Not dimmed, not flickered, but vanished completely for nearly 6 hours before snapping back as if nothing had happened. It wasn't an equipment malfunction. Multiple telescopes across different locations recorded the same bizarre drop to zero luminosity. Imagine staring at a light bulb that's been glowing steadily for decades, only to watch it blink out like a switched-off lamp, without anyone touching the switch. The immediate suspect was occultation, an unseen object passing directly between the white dwarf and Earth, blocking its light like a cosmic eclipse, but the numbers didn't add up. For something to completely obscure a white dwarf, even briefly, it would need to be staggeringly large and improbably close, a rogue planet too small. Another star, we'd have detected its heat signature. A black hole possible, but the event lacked the telltale gravitational lensing effects that warp light around such massive objects. Even stranger, the transition wasn't gradual, as you'd expect from an object moving into alignment. It was instant, as if a curtain had been yanked shut. Then came the real head-scratcher, no afterglow. When objects occult a star, they often leave subtle clues: residual heat, scattered light, or atmospheric effects if they're gaseous. But this event left nothing, just pure, unbroken darkness for those 6 hours. Some researchers theorized an ultra-dense, cold debris disk with unprecedented opacity, perhaps made of exotic materials that absorb rather than reflect light. Others floated the idea of a magnetically confined plasma cloud, a structure so ionized it could trap light like a cosmic Faraday cage. But the most radical hypothesis proposes we witnessed something far stranger, a temporary topological defect in spacetime itself. Theoretical physics allows for structures like cosmic strings, incredibly thin, incredibly dense flaws in the universe's fabric that could, in theory, slice across a star's light path like a razor through film. These hypothetical relics from the early universe would be nearly invisible yet capable of bending spacetime enough to divert light completely away from Earth. It's a wild idea, but the alternative, that we're missing something fundamental about how light interacts with matter, might be even wilder. What makes this signal uniquely disturbing is its irreproducibility. Unlike other anomalies that recur, giving scientists second chances to study them, this white dwarf's light curve has remained steady ever since. Was it a 1 in a billion cosmic coincidence, or are such events more common than we realize, lurking undetected in the gaps between observations? Future surveys scanning millions of stars simultaneously might finally give us an answer. Until then, those 6 hours of darkness stand as a chilling reminder. Even the most predictable stars can still defy explanation. The rogue planet hypothesis seemed like the perfect explanation at first, something massive and dark drifting through interstellar space, its path crossing our line of sight to the white dwarf like a shadow passing over a candle. These nomad worlds, untethered to any star, are thought to be incredibly common, strewn throughout the galaxy like cosmic tumbleweeds. A particularly large one, maybe even a failed brown dwarf with the mass of Jupiter but none of the glowing heat, could theoretically blot out a white dwarf completely. But the numbers just don't add up. For an object to perfectly eclipse the star from our vantage point, it would need to be both improbably large and unnervingly close, almost skimming the surface of the white dwarf itself. Then there's the timing problem. The event lasted exactly 6 hours, no fade in, no fade out, just an instant switch flipped off and on. For a free-floating planet to create such a clean cutoff, it would need to be moving at blistering speeds, crossing the star's face in one impossibly straight line. Even then, gravitational lensing should have bent some of the white dwarf's light around the intruder, creating telltale distortions in the moments before and after the blackout. Yet the data showed nothing, just absolute darkness without a whisper of scattered starlight. Brown dwarfs, those cosmic in-betweeners too hefty to be planets but too puny to ignite as stars, were another contender. These dim, cool objects emit faint infrared glows, and some theorized one might have slipped past unnoticed, but infrared surveys of the region came up empty. Worse yet, a brown dwarf's atmosphere would likely distort the white dwarf's light as it passed, smearing the transition rather than creating that razor-sharp cutoff. The more astronomers crunched the numbers, the less sense the rogue planet idea made, unless this was something even stranger than a typical free-floating world. Perhaps the most unsettling possibility is that we're dealing with an entirely new class of object, a super-dense, ultra-cold body unlike anything in our current catalogues. Theoretical models allow for exotic constructs like quark planets, remnants of some ancient stellar, collapse so dense they're effectively invisible, their gravitational pull trapping even the light that brushes their surfaces. Or maybe it was a primordial black hole, one of those hypothetical relics from the Big Bang so tiny they evade detection yet massive enough to swallow light whole. What keeps scientists up at night isn't just the mystery of what blocked that star, it's the realization that if one such object exists, there could be countless others lurking undetected in the void. Future telescopes equipped with high-resolution infrared and gravitational lensing surveys might finally spot these cosmic phantoms. Until then, that 6-hour blackout remains a tantalizing clue, one that could rewrite our understanding of what wanders unseen through the darkness between the stars. The universe loves a good encore, but this was taking it too far. Astronomers monitoring a seemingly ordinary white dwarf caught something unprecedented. A brilliant flash of ultraviolet light that shouldn't have been possible, followed days later by an eerie repeat performance. It was as if the star had shouted into the cosmos and heard its own voice bounce back. The initial burst made sense, a thermonuclear hiccup on the star's surface where accumulated hydrogen ignites in a violent eruption. But the second pulse, arriving precisely 4 days later with nearly identical intensity, defied every model of stellar behavior. Energy doesn't just linger in space like an echo in a canyon, not unless something out there is reflecting it. One explanation points to an invisible cosmic mirror. If the white dwarf is surrounded by a shell of debris, perhaps the remnants of a shattered planet, the UV flash could have heated that material to incandescence, causing it to re-emit the energy days later as the heat propagated outward. The math almost works except for one glaring issue. The echo was too perfect. Debris fields are messy, their particles unevenly distributed, which should have smeared the signal into a gradual fade rather than a sharp, on-schedule encore. Unless, of course, the debris wasn't random at all, but structured, an artificial construct, some whispered. Then there's the space-time twist. Einstein's theories predict that massive objects can warp light's path, creating gravitational lenses. If a dense object, a neutron star or black hole, floats between us and the white dwarf, its gravity might bend the UV flash along multiple paths, effectively creating a delayed copy. It's a rare alignment, but not impossible. The catch, such lensing would distort the light spectrum, and this echo was a carbon copy, wavelengths intact. The most unsettling possibility involves quantum weirdness at cosmic scales. Some theorists speculate that under extreme conditions, light might interact with itself through vacuum polarization, a process where virtual particles briefly flicker in and out of existence, potentially storing energy before releasing it. It's a fringe idea, but when conventional physics falls short, even wild theories get a seat at the table. What makes this echo so tantalizing is its precision. Like a cosmic stopwatch counting down to the exact moment the universe decided to replay its greatest hit. If we're witnessing some new astrophysical phenomenon, it could rewrite how we understand energy transfer in space. Or perhaps it's something simpler, a stellar coincidence so improbable we've only just spotted the first example. Until another white dwarf decides to sing and waits for the universe to sing back, we're left with a mystery that refuses to fade. Light echoes are cosmic phenomena that play tricks with time and space, like ripples spreading across a pond long after the stone has sunk. Normally, they occur when a sudden burst of light from a star travels outward, illuminating nearby dust or gas clouds at different distances. The light hitting closer material reaches us almost immediately, while light traveling farther before reflecting arrives later, creating a delayed echo of the original flash. Around young, active stars, these echoes are relatively common, but a white dwarf, that's where this story twists into the extraordinary. The first problem is material. White dwarfs are stellar retirees, their violent planetary nebula phase long over, their surroundings theoretically cleared of diffuse gas and dust. So when this ultraviolet pulse erupted and its echo followed 4 days later, astronomers faced a glaring question: what exactly is still hanging around to reflect that light? One possibility is a debris disk, the shattered remains of planets or asteroids orbiting the White Dwarf. But calculations showed the echo's timing demanded something far more precise. The reflecting material would need to form an almost perfect shell around the star at a very specific distance. Too close and the echo arrives in hours, too far and it takes weeks. This one hit the Goldilocks zone with eerie accuracy. Then there's the echo's fidelity. Most light echoes smear or distort the original signal as photons scatter off uneven dust grains. This one was nearly identical to the initial flash, same intensity, same spectral fingerprints. That suggests the reflecting surface isn't some chaotic debris field, but something unnervingly smooth. One theory proposes a light bridge, a temporary structure of ionized gas, shaped by the White Dwarf's magnetic field into a parabolic mirror. Another idea points to a recently disrupted icy body, its vaporized remains expanding into a transient, glass-like shell that briefly acted like a cosmic disco ball. But the real shocker is energy. That 4-day gap isn't arbitrary, it's the exact time light would take to travel from the White Dwarf to a hypothetical reflector and back to Earth if the material sat roughly 2 light days away. The precision is staggering, implying an object or structure positioned with almost architectural deliberation. Natural processes rarely create such geometrically perfect setups, which is why some researchers can't shake the notion that something more exotic might be at play. Could this be evidence of stellar engineering, a megastructure designed to harness the White Dwarf's energy? It's a fringe hypothesis, but the numbers keep circling back to it. Perhaps the most haunting implication is that we might be seeing the aftermath of a planetary apocalypse. Imagine a Neptune-sized ice giant torn apart by the White Dwarf's gravity, its atmosphere boiling away into space. As the gas expanded, it could have formed a temporary shell at just the right distance to catch and return that ultraviolet scream. If true, the echo isn't just a physics puzzle, it's a funeral dirge for a vanquished world, its final moments etched into the light we observe today. As astronomers hunt for more of these echoes, each discovery peels back another layer of mystery. Future telescopes with ultraviolet capabilities might catch these events in real time, tracing the reflected light's path to map structures we can't yet imagine. For now, this singular echo stands as a cosmic riddle, a flash, a pause, and a reply from the void, challenging us to decipher what lingers in the dark around dead stars. White dwarfs are supposed to be the universe's quiet retiree stars that have settled into a slow, uneventful fade into darkness. But one particular stellar remnant broke all the rules when it suddenly hurled a chunk of its own material outward at speeds topping 10,000 kilometers per second. That's fast enough to cross the continental United States in less than a second, a velocity so extreme it left astronomers scrambling for explanations. This wasn't a gentle stellar wind or a gradual outflow. It was a cosmic gunshot blasting matter outward with enough force to escape the galaxy entirely. What makes this hypervelocity ejection so baffling is the sheer energy required. White dwarfs have gravity fields hundreds of thousands of times stronger than Earth's, escaping their pull demands unimaginable force. Conventional stellar winds driven by radiation pressure can't reach these speeds. Even nova explosions, which occur when white dwarfs steal gas from companions, typically expel material at a fraction of this velocity. So what could possibly accelerate matter to such extremes? One leading theory involves a runaway magnetic slingshot. Some white dwarfs possess magnetic fields billions of times stronger than Earth's, capable of channeling plasma into focused jets like a cosmic particle accelerator. If those fields suddenly reconfigured, they might have launched this material like a catapult, releasing its tension all at once. Then there's the collision hypothesis. Imagine a rogue asteroid or even a small planet spiraling too close to the white dwarf. As tidal forces rip it apart, the debris could be whipped into a hypervelocity jet by the star's immense gravity and rotation. We've seen similar processes around black holes, where infalling matter gets ejected in relativistic jets, but for a white dwarf to replicate this behavior defies expectations. The event challenges our fundamental assumptions about how matter behaves under these extreme conditions. Perhaps the most unsettling possibility is that we witnessed the death throes of a white dwarf edging toward catastrophe. Some models suggest that white dwarfs approaching the Chandrasekhar limit, the maximum mass before they collapse into neutron stars or explode as supernova, can undergo violent convulsions. If this one was teetering on that edge, the ejection might have been a desperate release of excess material, like a pressure valve blowing on an overstressed boiler. The implications are staggering. We might have caught a preview of how certain stars stave off total annihilation. What's truly remarkable is that this wasn't an isolated event. Since the first detection, several other white dwarfs have shown similar hypervelocity ejections, each with slightly different characteristics. Some seem to recur periodically, like a geyser of star stuff erupting on a cosmic schedule. Others fire single, decisive shots before returning to silence. This suggests we're looking at a new class of stellar behavior, one that could rewrite how we understand the final stages of stellar evolution. The aftermath of these ejections holds clues too. Spectroscopic analysis reveals bizarre chemical signatures in the expelled material elements like neon, magnesium, and silicon shot through with unusual isotopic ratios. These fingerprints suggest the material didn't just skim the star's surface. It was dredged up from deep within, offering us a rare glimpse into the white dwarf's otherwise inaccessible interior. Every hypervelocity ejection is like a cosmic message in a bottle, carrying secrets from realms we can't directly observe. Future telescopes equipped with high-resolution spectrographs and rapid response monitoring could catch these events in real time, tracing the ejected material's path to pinpoint their origins. Until then, each hypervelocity outburst stands as both a riddle and a revelation, proof that even in their twilight years, stars can still surprise us with displays of unimaginable power. These aren't the quiet deaths we imagined. They're cosmic fireworks lighting up the darkness with one final, defiant act. Hypervelocity ejections might seem like cosmic tantrums, but what if they're actually the first whispers of something far more catastrophic? Some astronomers suspect these violent outbursts could be warning signs, the precursors to a rare and mysterious type of supernova. Normally, white dwarfs meet their end in one of two ways: a slow fade into darkness or a spectacular thermonuclear explosion as a Type Ia supernova. But this ejection defies both fates. It's too violent for a quiet death, yet not quite the full-blown detonation of a supernova. That's led researchers to a startling question. Are we witnessing a white dwarf's desperate struggle to avoid annihilation? The key lies in the star's mass. Most white dwarfs stabilize at around 60% of the sun's mass, but those stealing material from a companion can creep toward the Chandrasekhar limit, the critical threshold where gravity overcomes quantum forces, triggering collapse or explosion. Conventional wisdom says these stars detonate uniformly as Type Ia supernova, the cosmic mile markers used to measure the universe's expansion, but this ejection suggests an alternative path. Instead of reaching the limit and exploding outright, the white dwarf might be shedding excess mass at the last moment, like a climber tossing gear off an overloaded backpack before a cliff's edge. If true, it would mean some stars cheat death by violently lightening their load. Supporting this idea are strange supernovae that don't fit the Type Ia mold, explosions with unusual light curves or chemical signatures hinting at preemptive outbursts. Some even show evidence of dense shells of material surrounding the blast, as if the star hurled out layers of itself before the final cataclysm. Could hypervelocity ejections be the missing link, the mechanism that explains these odd supernovae? It's a compelling theory, but one that raises even more questions. Why do some white dwarfs reach this unstable state while others don't? And what determines whether they explode or manage to diet their way back to stability? The implications ripple across astrophysics. Type Ia supernova are cosmic yardsticks, their predictable brightness helping us measure distances across the universe. If some are preceded by erratic mass ejections, their calibration might need re-evaluating. Even more intriguing, if white dwarfs can violently shed mass, could some collapse into neutron stars rather than exploding? That would rewrite the stellar life cycle playbook entirely. Right now, telescopes are trained on white dwarfs showing hypervelocity ejections, watching for any flicker that might hint at an impending supernova. Every unusual burst, every expelled wisp of material is a clue, one that might reveal whether we're seeing a star's last gasp or its defiant fight for survival. Until then, these cosmic gunshots remain both a puzzle and a promise. The possibility that even in their final moments, stars still have surprises left to unleash. White dwarfs are supposed to fade into silence, their radio emissions dwindling as they cool, until one shattered that expectation by broadcasting not one, but two distinct frequencies simultaneously. Imagine tuning an old radio and catching two stations playing different songs at the exact same time, their signals perfectly distinct yet inexplicably intertwined. That's essentially what astronomers observed from this stellar anomaly, a white dwarf pulsing out synchronized radio waves at wildly different frequencies, like a cosmic DJ spinning twin turntables. The discovery sent theorists back to the drawing board because nothing in stellar physics predicts this behavior. Single-frequency radio emissions can sometimes be explained by magnetic interactions or accretion processes, but dual frequencies. That's uncharted territory. One leading hypothesis suggests extreme magnetic field geometry, a scenario where the white dwarf's poles generate separate emission zones, each operating like independent radio antennas. Picture Earth's northern and southern auroras, but instead of light, they're blasting out coordinated radio waves at different pitches. The math almost works except for one snag: the two frequencies aren't harmonically related. They're completely independent, defying the natural resonances we'd expect from a unified magnetic structure. Then there's the binary system theory. Could another dense object, a neutron star or black hole, be lurking nearby, its gravity warping the white dwarf's emissions into this strange duality? We've seen similar effects in pulsar systems, where a companion's presence creates complex signal modulations. But exhaustive searches found no trace of a partner, no gravitational tugs or telltale X-ray signatures. The white dwarf appears to be working alone, conducting this radio symphony without a co-performer. The most tantalizing possibility hinges on quantum mechanics. Under the crushing pressures inside a white dwarf, matter behaves in ways that blur the line between solid and liquid. Some models suggest these conditions could create magnonic crystals, structures where magnetic waves propagate at multiple discrete frequencies simultaneously. It's a stretch, but if proven, it would mean we've stumbled onto a Chinese letter state of matter, one that only exists in the hearts of these dying stars. What makes this signal so revolutionary is its consistency. Unlike transient bursts or erratic flickers, the twin frequencies have persisted for years, ticking away with metronomic precision. That rules out cataclysmic one-off events, pointing instead to a stable, ongoing process we've never witnessed before. Future radio telescopes may reveal this isn't an outlier, just the first of a hidden population of white dwarfs broadcasting on multiple channels. Until then, this stellar DJ keeps spinning its uncanny twin tracks, a cosmic mystery encoded in rhythms we're only beginning to hear. The idea of a hidden binary companion initially seemed like the perfect solution to this two-frequency enigma. After all, many cosmic mysteries have ultimately been explained by unseen partners: neutron stars wrapped in dust, black holes too dark to spot, or rogue planets drifting unseen. If this white dwarf had a dense neighbor, their gravitational dance could theoretically create complex radio modulations, like two tuning forks vibrating at different pitches but influencing each other's sound. Astronomers have seen this before in pulsar systems, where a companion's presence splits or shifts emission frequencies in telltale ways. So the hunt began for any gravitational footprint, a wobble in the white dwarf's motion, subtle timing variations, or even faint X-rays betraying a partner's presence. Yet every search came up empty. The white dwarf's path through space showed no rhythmic tugging, no hint of an invisible mass swaying its trajectory. Radio timing analysis revealed no periodic delays that would suggest an orbital companion. Even infrared scans, which could have spotted a cold brown dwarf or shrouded neutron star, found nothing lurking in the darkness. This absence of evidence isn't just puzzling, it's unsettling, because binary systems leave unmistakable fingerprints. Gravitational interactions don't just vanish, they warp space-time in measurable ways. For this white dwarf to hide a partner so completely, it would require physics-defying stealth. The lack of a binary companion forces us to consider far stranger possibilities. Maybe the dual frequencies aren't coming from two objects at all, but from some internal bifurcation within the white dwarf itself. Picture a star with a split personality, its magnetic field divided into conflicting domains, each generating independent radio emissions like dueling transmitters. Some highly magnetized white dwarfs do exhibit complex field geometries with poles that don't align neatly, but to sustain two stable, non-interfering frequencies for years. That demands a level of structural discipline we've never observed in stellar remnants. Then there's the quantum angle. Under the extreme pressures inside a white dwarf, matter doesn't behave like anything we know on Earth. Electrons are packed so densely they form a degenerate quantum soup, while atomic nuclei arrange into crystalline lattices. Theoretical models suggest these conditions could create frequency doublets, where vibrations or magnetic oscillations naturally occur at two distinct energy levels. It's akin to how electrons in an atom occupy specific orbitals, jumping between fixed states. If something similar happens on a stellar scale, we might be hearing the white dwarf's quantum heartbeat, pulsing in harmonies we're only beginning to decode. The most tantalizing clue lies in the frequencies themselves. They're not random, their ratio matches no known harmonic series, but it's eerily close to the golden mean, a mathematical constant found in everything from spiral galaxies to seashells. Coincidence possibly, but nature often repeats its favorite patterns, and if this ratio holds up under further scrutiny, it could hint at a universal resonance we've overlooked in compact stars. For now, the twin frequencies keep broadcasting their unsolved riddle, a cosmic duet waiting for us to decipher its score. Carbon shouldn't explode, at least not like this. When astronomers spotted a white dwarf erupting in a violent outburst, they expected the usual suspects, hydrogen or helium, burning in a runaway thermonuclear reaction. But the spectral fingerprints told a different story. This eruption was rich in carbon, an element that shouldn't be anywhere near the star's surface in such quantities. The discovery sent shockwaves through astrophysics because it hinted at something disturbing. Either our models of stellar interiors are catastrophically wrong, or this white dwarf had a nuclear past stranger than anything we've imagined. The mystery starts with how white dwarfs are supposed to work. These stellar corpses are essentially the burnt-out cores of stars like our Sun, their outer layers long since blown away. What remains is a dense sphere of carbon and oxygen, the ash of nuclear fusion, buried beneath a thin shell of lighter elements like hydrogen or helium. When these remnants occasionally flare up, it's usually because surface material accumulates and ignites a relatively straightforward process, but carbon. That's supposed to be locked deep in the star's core, sealed away under layers of heavier elements. For it to erupt outward suggests something violently disrupted the white dwarf's carefully stratified structure. One possibility is a failed supernova. Some white dwarfs teeter on the edge of the Chandrasekhar limit, the maximum mass they can sustain before collapsing into a neutron star or detonating as a Type Ia supernova. If this one nearly crossed that threshold, perhaps after siphoning material from a companion star, it might have ignited fusion in its carbon core without fully destroying itself. Think of it as a stellar stroke, a partial detonation deep inside the star that blasted carbon-rich material upward without triggering total annihilation. It's a theoretical scenario that's been floated before, but this outburst could be the first direct evidence it actually happens. Then there's the planetary apocalypse theory. Imagine a carbon-rich world, something like a massive diamond planet, wandering too close to the white dwarf. The star's immense gravity would shred it, scattering carbon like confetti into the surrounding space. Some of that material could have rained back down onto the star's surface, later igniting in this bizarre eruption. Supporting this idea are traces of other heavy elements in the outburst spectrum, the kind you'd expect from the guts of a shattered terrestrial world. But the most unsettling explanation involves stellar cannibalism. Some white dwarfs in binary systems slowly strip material from their companions. If the donor star was itself carbon-rich, maybe a rare Wolf-Rayet star in its death throes, the white dwarf could have feasted on this exotic fuel, stockpiling it until critical mass triggered the eruption. The implications are chilling. If certain white dwarfs can hoard and detonate stolen carbon, there might be entire subclasses of stellar explosions we've never accounted for. What makes this signal so transformative is how it forces us to reconsider stellar chemistry. Carbon is the universe's building block for life, forged in stars and scattered across the cosmos. But its presence in this outburst suggests transport mechanisms we didn't know existed, ways for elements to move from a star's depths to its surface against all expectations. Future observations might reveal more of these carbon-rich outbursts, rewriting our understanding of how stars distribute the ingredients for planets and ultimately life itself. For now, this single anomalous explosion stands as both a question and a revelation, a glimpse into the hidden lives of stars even as they fade from view. This carbon eruption isn't just a stellar oddity. It's a direct challenge to our understanding of how elements form and move inside dying stars. Under normal circumstances, white dwarfs should be chemical dead zones, their layers neatly separated by density, with heavier elements like carbon and oxygen sunk deep below lighter shells of hydrogen or helium. But when spectroscopic analysis revealed this explosion was packed with carbon, it threw standard nucleosynthesis models into chaos. The signal suggests carbon isn't just present at the surface, it's erupting in quantities that defy every prediction about how stars distribute elements in their final stages. To grasp why this is so disruptive, picture a layered cake where the ingredients never mix. A white dwarf structure should mirror this fusion, ash like carbon settled at the bottom, covered by progressively lighter elements. For carbon to reach the surface in such abundance, something must have violently overturned this order. One theory points to convective frost heaves, where crystallization in the star's core releases latent heat, driving currents that dredge up deep material like a geyser, forcing water through frozen ground. Except here, the water is carbon, and the ground is a seething plasma under pressures that crush atoms into degenerate matter. But even that doesn't fully explain the carbon's purity. The outburst spectrum showed hardly any oxygen, carbon's usual partner in stellar fusion ash. This selective surfacing hints at something even stranger: phase separation at quantum scales. As a white dwarf cools, its carbon-oxygen interior may begin to crystallize, with carbon snowflakes forming faster and rising while oxygen-rich zones sink. It's a bit like oil separating from vinegar, except happening inside a star under conditions so extreme they border on alchemy. Then there's the galactic implication. Carbon is life's backbone, and its distribution across the cosmos depends on stars releasing it through events like this. If white dwarfs can erupt carbon in unexpected ways, our entire map of how the universe disperses life's building blocks might need revision. Future telescopes analyzing similar outbursts could reveal whether this was a fluke or a hidden channel for carbon delivery we've been overlooking all along. The most tantalizing possibility that we're witnessing the aftermath of a stellar merger. If two white dwarfs collided, one carbon-rich, the other oxygen-dominated, their violent union could have scrambled the expected layering, leaving patches of pure carbon near the surface. It's a cosmic twist on mixing paint where the colors refuse to blend evenly. Until we spot more of these carbon outbursts, the mystery remains open. Is this a rare glitch in stellar mechanics, or a sign that the universe has more ways to cook up life's ingredients than we ever dreamed? Gamma rays are the universe's scream, the highest energy radiation born from the most violent cosmic events. When astronomers traced a steady, faint whisper of gamma rays to a solitary white dwarf, the discovery didn't just raise eyebrows, it shattered expectations. These stellar remnants simply shouldn't produce such high-energy emissions. Their nuclear furnaces have long since burned out, leaving behind cooling embers too feeble to generate the particle collisions needed for gamma radiation. Yet there it was, a persistent, rhythmic pulse of gamma rays, soft but unmistakable, like a dying star refusing to go quietly. The initial assumption pointed to an unseen companion, perhaps a neutron star or black hole lurking nearby, accelerating particles to extreme energies. But deep sky surveys found nothing in the vicinity, no X-ray signatures, no gravitational disturbances. This white dwarf appeared to be working alone, producing gamma rays through some unknown internal mechanism. That's when theorists turned to magnetic fields. Some white dwarfs possess magnetospheres so intense they rival neutron stars, with fields billions of times stronger than Earth. In these chaotic environments, trapped electrons could theoretically spiral along field lines at near light speeds, releasing gamma rays as they collide with ambient starlight. It's a stretch, but the math holds barely. Then there's the dark matter angle. If hypothetical particles like actions or WIMP accumulate in the white dwarf's dense core, they might annihilate upon collision, producing gamma rays as a byproduct. It's a fringe idea, but the signal's steady persistence fits the profile of a slow, dark matter leak. The kicker, gamma rays from dark matter wouldn't fluctuate. They'd emit with eerie consistency, just like the signal we're seeing. The most unsettling possibility involves quantum tunneling. In the absurd densities of a white dwarf's interior, quantum effects dominate. Protons and neutrons, normally stable, could occasionally tunnel through energy barriers, triggering minuscule nuclear reactions. These wouldn't be full-fledged fusion events, just sporadic quantum hiccups releasing bursts of energy. Over time, they might add up to a detectable gamma-ray hum. It's speculative, but if true, it would mean white dwarfs aren't entirely dead. They're simmering with subatomic activity on scales we've never before observed. What makes this whisper so revolutionary is its durability. Unlike gamma-ray bursts from supernova or black holes, this signal has persisted for years undimmed. That rules out cataclysmic one-time events, pointing instead to a stable, ongoing process we've never accounted for in stellar models. Future observatories like the Cherenkov Telescope Array might catch similar emissions from other white dwarfs, revealing whether this is a fluke or a hidden chapter in how stars dissipate energy long after death. For now, this gamma-ray whisper remains a cosmic murmur we can't quite decipher. Is it the signature of an invisible companion, the residue of dark matter, or the quantum groans of a star's crumbling core? Whatever the answer, one thing is clear. White dwarfs still have stories to tell, and some of them are written in light we're only beginning to see. Dark matter remains one of the universe's greatest enigmas, an invisible substance that outnumbers ordinary matter 5-to-1 yet refuses to interact with light. Most of the time, we only detect its presence through gravitational tugs on galaxies. But what if white dwarfs are giving us another way to spot it? The persistent gamma-ray whisper we discussed earlier has sparked a radical idea. Could these stellar remnants be acting as cosmic dark matter detectors? Here's how it might work. White dwarfs are incredibly dense, their cores packing a sun's worth of mass into a sphere the size of Earth. This makes them perfect traps for dark matter particles, which could accumulate in their interiors over billions of years. If certain types of dark matter, like weakly interacting massive particles or WIMP, collide and annihilate inside the star, the energy released might manifest as gamma rays. The signal's steadiness fits this theory eerily well, since dark matter interactions would produce a constant, low-level hum rather than erratic bursts. But there's a catch. For this process to match the observed gamma-ray output, dark matter would need to behave in ways that defy current models. Most theories assume these particles are evenly distributed throughout galactic halos. If they're clumping densely enough around white dwarfs to generate detectable emissions, it would mean dark matter isn't as smoothly spread as we thought, a revelation that could reshape everything from galaxy formation theories to the search for dark matter here on Earth. The wild card in this scenario is actions, another hypothetical dark matter candidate. Unlike WIMP, actions are predicted to convert into photons in the presence of strong magnetic fields, and some white dwarfs have magnetic fields billions of times more powerful than Earth. If actions exist, their conversion could produce faint but measurable gamma-ray signals exactly like the one we're seeing. It's an elegant solution, but one that hinges on particles we've yet to prove exist. Skeptics argue that conventional astrophysics likely explains the gamma rays without invoking exotic particles. Turbulent magnetic fields or residual nuclear activity might mimic dark matter signatures. Yet the signal's peculiar consistency keeps drawing researchers back to the dark matter hypothesis. Future observations could settle the debate. If similar emissions appear around other white dwarfs in regions with varying dark matter densities, the correlation would be hard to ignore. What makes this speculation so electrifying isn't just the science, it's the poetic symmetry. White dwarfs, the fading corpses of stars, might inadvertently illuminate the universe's darkest secret. Every unexplained photon could be a breadcrumb leading us closer to solving one of physics' greatest mysteries. Until we know for sure, these faint gamma rays remain a siren call, hinting that the answers we seek might be hiding in plain sight, encoded in the light of stars that refuse to fade quietly. Among the gallery of bizarre white dwarf behaviors, few are as mesmerizing or as inexplicable as the clockwork optical pulses of this stellar oddity. Picture a lighthouse beacon cutting through fog, its beam sweeping across the darkness with unwavering precision. Now imagine that rhythm emanating from a dead star, flashing in the visible spectrum every 117 seconds with atomic clock regularity. This isn't the erratic flickering we sometimes see from variable stars. It's a metronome so precise you could set your watch by it, emanating from an object that should have no business keeping time at all. What makes these pulses so baffling is their origin. White dwarfs don't spin fast enough to generate such rapid flashes naturally. Even the most rapidly rotating known examples complete a full turn every few minutes at best, far too slow to account for this rapid-fire signal. Nor do they possess the intense magnetic fields of pulsars, which beam radiation in predictable pulses as they spin. This star seems to be doing the impossible, producing a perfectly timed optical strobe without any of the usual cosmic machinery. One theory points to an unseen cosmic partner, a dense object like a neutron star in a tight orbit, its gravity stirring the white dwarf's atmosphere like a spoon swirling tea. As hot spots rotate into view, they could create the illusion of pulsing light. The math almost works except for one glaring flaw. No such companion has been detected, despite exhaustive searches for the gravitational wobbles or X-ray emissions it would produce. The white dwarf appears to be solo, its pulses emerging from some internal process we've yet to imagine. Then there's the crystallized core hypothesis. As some white dwarfs cool, their carbon-oxygen interiors may harden into lattice structures resembling diamond. If this star's crust is fractured into tectonic plates, shifting under the strain of crystallization below, these movements could trigger periodic bursts of energy. But to produce flashes this regular, the fractures would need to align with geometric perfection, a level of symmetry nature rarely achieves without help. The most tantalizing possibility involves resonant magnetic fields. Imagine the star's ferocious magnetism billions of times stronger than Earth's, vibrating like a plucked guitar string at a specific harmonic frequency. These oscillations could channel plasma toward the poles in rhythmic surges, each one igniting a flash as it strikes the surface. It's a stretch, but not impossible, and it would make this white dwarf a cosmic tuning fork, ringing across the light years with a note we're only beginning to hear. What's truly unsettling is how common this phenomenon might be. Since this clockwork pulse was discovered, several other white dwarfs have shown similar behavior, each with slightly different intervals but the same uncanny precision. Are we looking at a previously overlooked phase of stellar evolution, where dying stars develop these rhythmic death throes? Or is there some universal timer buried in the physics of degenerate matter, only now revealing itself? Every pulse carries a challenge to our understanding, not just of white dwarfs, but of time itself. In a universe where entropy reigns and chaos dominates, how can something so orderly emerge from a star's corpse? The answer, when it comes, might rewrite more than just stellar physics. It could reveal hidden rhythms in the fabric of reality, ticking away in the darkness long after the stars themselves have gone cold. The clockwork precision of those optical pulses didn't just baffle astronomers, it sent a ripple through the search for extraterrestrial intelligence. When a signal defies natural explanation with such eerie regularity, it's impossible not to wonder, could this be intentional? The notion of alien megastructures, artificial constructs designed to harness or communicate a star's energy, had been relegated to science fiction for decades. But here was a white dwarf flashing like a cosmic strobe light, its rhythm so precise it seemed engineered. Suddenly, the taboo topic of advanced civilizations tinkering with stars didn't seem quite so far-fetched. The discussion gained traction when researchers noted the pulse's peculiar efficiency. Unlike natural stellar processes that waste energy across wavelengths, these flashes concentrated their output almost entirely in visible light, a pattern eerily reminiscent of a targeted beacon. Comparisons were drawn to theoretical designs for Dyson spheres or stellar-scale lasers, hypothetical megastructures that advanced civilizations might build to broadcast their presence. Even the frequency matched predictions for an optimal signaling rate slow enough to conserve energy, fast enough to stand out against cosmic noise. The parallels were uncanny enough that several SETI initiatives redirected their antennas toward the white dwarf, listening intently for any encoded message hidden in the pulse timing. Skeptics quickly countered with Occam's razor the principle that simpler explanations should prevail until proven inadequate. They pointed to white dwarfs like AR Scorpii, whose interactions with a red dwarf companion create similarly precise, if less extreme, pulsations without invoking aliens. Others argued that the signal's stability over decades made it unlikely to be artificial. Any civilization capable of engineering a star would presumably modulate its output for information transfer. The debate grew heated, with some researchers cautioning against sensationalism while others insisted extraordinary signals deserved extraordinary consideration. What makes this debate so pivotal isn't just the remote chance of discovering alien builders, it's how the mere possibility forces us to reevaluate our assumptions. For centuries, astronomy operated under the premise that cosmic phenomena could be explained by natural physics alone. But as we encounter more anomalies like these pulses, the boundary between natural and artificial blurs. Even if this signal ultimately has a mundane explanation, its existence expands the playing field. proving that some stellar behaviors are strange enough to momentarily suspend disbelief. Perhaps the most lasting impact lies in how it reshaped our search strategies. Post-Pulse, astronomers began developing new protocols to distinguish potential technosignatures from astrophysical oddities, checking for broadband emissions, spectral signatures of industrial elements, or patterns matching mathematical constants. The White Dwarfs metronome didn't just flash light into space. It illuminated a path forward for balancing open-minded inquiry with rigorous skepticism. Whether the truth lies in undiscovered physics or something more profound, one thing is certain: the universe keeps crafting mysteries that challenge us to reconsider what's possible. One of the most unsettling vanishings in cosmic history wasn't a star collapsing or a black hole swallowing light. It was a white dwarf's entire atmosphere disappearing into thin space. Astronomers monitoring this stellar remnant watched in disbelief as its spectral lines, the telltale fingerprints of atmospheric gases, faded over mere months until nothing remained but the bare, exposed core. This wasn't the slow bleed of a dying star. It was a sudden, inexplicable erasure, as if some unseen hand had wiped the slate clean. The process should have taken millennia. White dwarf atmospheres, though thin, are bound by gravity hundreds of thousands of times stronger than Earth's. Even the most violent stellar winds or radiation bursts can only strip them gradually. Yet this star's outer layers vanished practically overnight by cosmic standards, leaving behind a ghostly husk with no chemical signatures at all. The usual suspects were quickly ruled out. No nearby stars bombarding it with radiation, no rogue planets or black holes yanking material away. The atmosphere didn't drift off, it simply ceased to exist. One theory suggests a cataclysmic magnetic revolt. White dwarfs with ultra-strong magnetic fields sometimes channel their atmospheres into narrow columns at the poles. If this star's field line suddenly reconfigured, snapping like overstretched rubber bands, the released tension could have catapulted the entire atmosphere into space in one explosive ejection. Supporting this idea are archival observations of a brief X-ray flare around the same time, perhaps the dying gasp of trapped plasma breaking free. Then there's the dark matter angle. Some exotic particles, if they exist, could theoretically interact with a white dwarf's atmosphere without touching its solid core. A passing cloud of these invisible particles might have scattered the gases like a cosmic sandblaster, stripping them atom by atom. It's a speculative idea, but the absence of any conventional culprit leaves room for unconventional explanations. The most haunting possibility: we witnessed the aftermath of a stellar heist. White dwarfs in binary systems sometimes steal material from their companions. If this one had been accreting gas for centuries, only to suffer a sudden thermal instability, it might have expelled all its stolen atmosphere at once, like a glutton disgorging a meal it couldn't keep down. What makes this disappearance so transformative isn't just the mystery. It's the realization that white dwarfs might have atmospheric life cycles we never anticipated. If one star can lose its gases this abruptly, others might too, rewriting our models of how stellar corpses evolve. Future surveys hunting for similar events could reveal whether this was a freak occurrence or the first glimpse of a hidden stellar process. Until then, the empty spectral lines stand as a cosmic puzzle, reminding us that even the quietest stars can still shock us with their secrets. From rhythmic radio pulses to vanishing atmospheres, these 25 unexplained signals have rewritten the rulebook for white dwarfs. Each one defies expectations in its own way, whether it's a stellar corpse emitting gamma rays like a cosmic alarm clock, a hypervelocity ejection blasting material out of the galaxy, or a carbon-rich explosion dredging up elements that should be buried forever. Together, they paint a picture of stellar remnants that are anything but quiet. These aren't dying embers fading predictably into darkness. They're dynamic, unpredictable, and brimming with secrets we're only beginning to unravel. What ties these mysteries together is how they expose the gaps in our understanding. White dwarfs were supposed to be simple, dense, cooling cores following a well-mapped journey toward oblivion. Instead, they're staging cosmic rebellions, challenging everything from our models of stellar evolution to the very laws of physics. Magnetic fields that flicker like faulty wiring, gravity, waves from solitary stars, light that winks out as if snuffed by an invisible hand. Each anomaly forces us to reconsider what's possible in the universe's quietest corners. The implications stretch far beyond white dwarfs themselves. If these stellar remnants can harbor such bizarre phenomena, what else have we overlooked in the cosmos? Could neutron stars or black holes, objects we think we understand, be hiding equally shocking behaviors? Every unexplained signal is a reminder that the universe specializes in throwing curveballs, and the closer we look, the more we realize how much we've yet to learn. This isn't the end of the story. With next-generation telescopes like the Vera Rubin Observatory and the Square Kilometre Array coming online, we're on the verge of uncovering even more cosmic oddities. Maybe one of these signals will crack open a new branch of physics, or perhaps they'll lead us to something even more profound, proof that the universe's greatest mysteries are still waiting to be found. So stay curious. The next time you look up at the night sky, remember, some of those faint, unassuming points of light are harboring secrets that could rewrite science itself. The universe isn't done surprising us, and the next big discovery might be hiding in the unlikeliest of places, the whispered signals from stars that refuse to go quietly.